Okay, so we have a problem here, one like we've been talking about in class, and I want to determine the displacement at C. You can see I have values of I, moment of inertia, and E of elasticity. Now, we could solve this problem in a lot of different ways. Direct integration, conjugate beam, but the one I want to demonstrate to you today will be virtual work. So remember our virtual work discussion. We need to write an equation for moment for this structure, and then we're going to do the virtual load, which, since we want displacement at C, there would be a unit load at C, and then write the equations for that. So that'll be the first two-thirds of the problem will be writing the moment equations for this and the virtual. So let's start here and find the real moments. So I guess the first thing we want to do is find our reactions. So very common in all of our problems are finding the reactions to start. So I'm going to sum moments about A, make sure the structure is in equilibrium. Right-hand rule for my moments. So looking at that, this 16 kip force is going to create what kind of moment about A? Positive or negative? Negative. So I'm going to have negative 16, that's the force, and the moment arm should be 10 feet. And then all the way over here on the right will be the moment produced by dy about A, and that looks like that's a positive moment, and the moment arm there is 40. So what is my reaction at D? It looks like it's going to be 4. So that's 4 kips. And then I can sum forces in the y direction. Excuse me. And when I do that, I have AY acting up. dy is acting up, and then my applied force 16 kips is down. So it looks like AY is going to be 12. So I have my reactions. Now, can I write one moment expression for the entire structure? Well, I could with special functions, but we're not approaching it that way. So I can write a simple expression that's valid from A to B, and then we have that discontinuity to worry about. And then a second expression that's good from B to D. And that's what I'll do. So the first one, going from A to B, that will be a region of X that's bounded by 0 to 10. And I'll draw a quick free body diagram of that segment. So my reaction, AY, is 12 kips. I have an internal bending moment to deal with, and what else? I think that's it, right? So if I sum moments about that cut surface, method of sections, I have the internal moment M, and then the reaction creates negative moment of 12 kips times X. So it looks like my moment for this expression, or this section, is 12X. Any questions about that? We only have one check we can do so far. We know the moment at A, since it's an external pin connection, is 0. So we take our expression for that region. If we put in X equals 0, it does predict the moment is 0. So far, so good. What about the second section? Well, that would be good from 10 to 40, this long 30-foot section. In that case, I think it's easier to look at the right-hand side of the cut. And in that case, I look at the reaction at dy, which is 4 kips. And of course, the distance from the left to the cut is X. And then the distance of our segment here would be the total distance, or total length of the beam, which is 40 minus X. So this will be 40 minus X. That's the distance here. And then again we have the internal bending moment. And again, that's all we have. So if I sum moments, again, at the cut, make sure I have an equilibrium. Looking at this segment, I have the internal moment, which is negative, and then the reaction at D, which will create positive moment about the cut. So that'll be 4 times the moment arm of 40 minus x. So my moment in this segment would be equal to 4 times 40 minus x. You can expand it if you like, but for right now I'm just going to keep it in this form. Now, in that segment, I do know the moment at a point at D. At the roller, I know that's 0, and that's at x equal 40. And if you plug in x equal 40, you do predict a moment of 0. Now, one last check we can do is, what's the moment at the point they share in common at 10? So I plug in 10 here, I get 120. And I plug in 10 here, and what do I get? 120. So they match. So I feel pretty good about that. So I think these are good expressions for the moment for the real load. So now what do I do? Yeah.
What do you mean when you say you can extend?
Oh, I could write this as 160 minus 44x, and I'm just going to leave it like this for now. So now let's do the virtual load. So I'll draw the beam. Same reactions, a pin and a roller. Now for this problem, I want the displacement at C, and C is right in the middle, so that means my virtual load will be right in the middle. So that will be located 20 feet from A and 20 feet from D. Now I'm assuming my virtual load is down, so that means I'm assuming my beam will deflect downward. Now, I don't think we need to go through this discussion, but if you looked at the reactions at AY and DY, I think you can see very easily that since the load is right in the middle, then half's going to go to one side and half's going to go to the other side. So I think I will shortcut it a little bit and tell you that this is going to be a half and that this one's going to be a half. Now, I need to write virtual moment expressions for this structure. Can I write one virtual moment equation that's valid for the whole structure? No. I can write one that's good from 0 to 20, that stops, and then I can write another one that's good from 20 to 40. So let's do that. So I'm going to now write an expression that's good for the first 20 feet. So I will cut this structure somewhere there, and I will work the left side. Excuse me. So if I look at a free body for that, I'll have my reaction at A, which is 1/2. My internal moment. Now this is the virtual moment, so I'm using the lowercase m for my notation, and it's at some distance x. So if I sum moments at the cut, set it equal to 0, right-hand rule for my sign convention, what do I get? Well, the internal moment is positive, and the moment created by the reaction at the left side is negative, and it'll be force 1/2 times distance x. So it looks like the virtual moment is simply just x over 2. We can do a quick check on that. So somewhere in the range from 0 to 20, do I know the moment? Yeah, I know it at the reaction here. It's what? 0. So when x is equal to 0, does my model predict that? Yes, it does. So far so good there. Now I'm going to cut the structure someplace over here, Going to work the left side or the right side? Right. So a politically balanced approach. Half left, half right. I thought that'd be a nice comment considering the silly season that we're in. Okay, so in the X direction, this is going to be good from 20 feet to 40 feet. So now I'm going to cut my structure. The right-hand side, dy, has a value of a half. There's the internal moment, lowercase. What's the distance of this segment? Remember, it's x to the cut. So it'll be the total distance, 40 minus x. So again, I'll sum my moments about the cut. And what do I have? Well, my internal moment is negative with that sign convention. And this force is positive times a moment arm of 40 minus x. So it looks like the virtual moment is equal to 1/2 40 minus x. Well, let's see if that works. So, do we know the moment somewhere in this second range? Yeah, out here at the roller. That's at x equal what? 40. You put in x equal 40, you get 0. The moment where these two match at x equal 20 should be the same. So I put 20 in here, I get 10. I put 20 in here, I get 10. So it seems like all my moment expressions are good. So really the hard work is done. Now we just need to put everything together. So remember now, with virtual work, the displacement at C is the integral over the length of m times the virtual moment divided by EI dx. And that would go from 0 to L. Okay, can I integrate from 0 to L? Well, some of my expressions are not valid for the full length. This one's only good for 10 feet. This is good for the next 30. This is good for the first 20 feet. This is for the next. So you're going to have to find segments where your real moments and your virtual moments match and collaborate. So this one's only good for 10 feet, real moment, and this one's good for 20. But I can use it for the first 10 feet, right? So this is going to end up being an integral from 0 to 10. The real moment is 12x. And what's the virtual moment from 0 to 10? X over 2. And I'm going to divide by EI. Alright, so I've only accounted for 10 feet of the total 40. So what comes next? Well, I have to go from 10 to what?
20.
Yeah, 20, because this equation is good up till 20, so I can continue to use it. But I have to switch my real moment to this equation. So my real moment now becomes 4 times 40 minus x times the virtual moment, x over 2. Oh, I almost forgot this thing. Divided by EI. And what's that integral good for? From 10 to 20. Now what about from 20 on? Well, my real moment's still good from 20 all the way to the end of the beam, but my virtual moment now switches from this first one to this second one. So I can finish it off. So I now go from 20 to 40. The real moment is still 4 times 40 minus x. The virtual moment is now this, 1/2 40 minus x. And divide by EI, which is constant for the whole structure, dx. So for me, on an exam, this is the answer. not on the exam, at home, working homework, this is not the final answer, right? I now have to actually do these integrals, evaluate them, sum the three terms up, then divide by EI and get a numerical value. Do you guys want to do that?
If we were doing the exam, we just leave it at that point?
Yeah.
Like we wouldn't have to write
Like on the exam, I might say, write the virtual work equation for the displacement at C, and this would be the virtual work equation. Now, if you look at this, we could probably do this in 4 or 5 minutes. I don't think it really demonstrates any unique talent. I think you guys can do these integrals given enough time. And although it's tedious, you could do this evaluation and add them all up. I think you can do that. So I won't take up any more class time with this on the video, but when I publish this problem online as a PDF of this piece of paper, I'll include a second page, and I'll go ahead and do the integrals, do the evaluation, give you a numerical value. But part of our discussion in class, I don't think we need to go any farther, unless you guys really need to see it. I think it'd be better to spend our time on applying the method to another problem than doing integrations of polynomials. I think you guys can probably do that one. So any other questions about this one before I stop it?